OpenGL has a pipeline architecture. Pipeline architectures are very common and can be found in many other application domains, such as an arithmetic pipeline. Imagine we want to multiply b with c and then add another value a to it, and we want to perform many such operations. So when two sets of a and b and c values are passed to the system, the multiplier can carry out the second multiplication without waiting for the adder to finish. So while adder is adding a1 to b1 and c1, the multiplier can basically multiply b2 and c2, which are the next bc values. This way the calculation time is shortened. The graphics pipeline basically follows the same principle. We have a vertex processor which processes the vertices, a clipper and primitive assembler, rasterizer, fragment processor, and then finally the pixels are displayed. So while the clipper is clipping the previous set of vertices, the vertex processor is already processing the next set of vertices. And this goes for the complete pipeline. While the fragment processor is processing the first set of vertices, the vertex processor has the fourth set of vertices to process. Objects passed to the pipeline are processed one at a time in order that they are generated by the application program. As a consequence of this, only local lighting effects can be generated. Hence, we cannot render shadows using such a pipeline. All steps of the pipeline can be implemented in the hardware on a graphics card. Let us look at what happens at the vertex processor. Much of the work in the pipeline is converting the object representations from one coordinate system to another. The objects are first defined in object coordinates. We must convert them to camera coordinates or the eye coordinates and subsequently convert them to screen coordinates. Every change of vertex coordinates is the result of a matrix multiplication being applied to the vertices. Vertex processor also computes the resulting color of the vertices. Perspective projection is the process that combines the 3D viewer with the 3D objects to produce the 2D image. Perspective projection is one such projection. In perspective projection, all projected rays meet at the center of the projection, so they have one common meeting point. In a parallel projection or orthographic projection, projected rays are parallel, they never meet, and the center of the projection is hence defined at infinity. In OpenGL, we can specify the direction of projection instead of the center of the projection to achieve this. This also happens at the vertex processor. Moving on to the next block of the pipeline, which is the primitive assembler and clipper. Vertices must be collected into a geometric objects before the clipping and rasterization can take place. These primitives are line segments, polygons, curves, and surfaces, which are formed by grouping of vertices in this step of the pipeline. Clipping is the process of removing objects or parts of objects that are not visible to the camera. Just as in the real world, cameras cannot see the whole world, virtual cameras can also not see the whole world. It only sees a part of the world that is visible to the lens. Objects that are not within its viewing volume are said to be clipped out of the scene. Look at this example where we have a perspective projection and all rays of light meet at one point, which is called the center of projection. In OpenGL, we can define a viewing volume with a front clipping plane and a back clipping plane. This combined with the center of projection produces a volume, and only objects that are inside this volume will remain after this clipper, and all other objects would be removed. The next block in the pipeline is the rasterizer. So what is rasterization? If an object is not clipped out, the approximate pixels in the frame buffer must be assigned colors. Rasterization produces a set of fragments for each object. Fragments are potential pixels. They are not finally qualified as pixels, but they are potential pixels. They have a location in the frame buffer. They have color, depth, and alpha attributes. Alpha is the last attribute in RGBA color, which is basically the transparency or opacity of the object. Vertex attributes are interpolated over the objects by the rasterizer so that the frame buffer is filled up. The final block of the pipeline is the fragment processor. Fragments are processed to determine the color of the corresponding pixel in the frame buffer. The color of a fragment can be determined by the texture mapping or by interpolation of vertex colors. Fragments may be blocked by other fragments closer to the camera. This is called hidden surface removal. Hidden surface removal is performed in the fragment processor.